So again, first and second derivative test, you need to know your justifications. If my function is increasing, how do we know? If my function is decreasing, how do I know where my relative maxes and mins are? We need to know all of our justifications, and now we're just doing it with true. Alright, so it asks us first for relative maximums, and we're just taking a look at number 2. So what is my justification for a maximum?
F prime is possible.
I heard f prime changes from negative to positive. Do we agree with that? If you don't, double check your board over here. So again, my relative max. Oh, what is that?
A min.
Good, that's a min. Okay, so let's flip-flop that. My maximum, I have a positive slope to a negative slope. Slope is my first derivative. Minimum, I have a negative slope to a positive slope. First derivative is my slope. Okay, so for min, we're going first derivative changes from negative to positive. Are we good with that? So that's what we have to look and see. Now, to find my even potential maxes and mins, or my critical values, I just simply check to see when my derivative is 0 when it's undefined. Then I need to check that on the number line to actually know when it changes signs. Alright, so let's go and do number 2 here with my relative max and mins. So I need my first derivative. Do I have negative cosine? Good, positive sine. Do I have negative 1/2 x? Good, negative 1/2. So for my first derivative test, I'm checking when it is 0 and also when it is undefined. Alright. So for when it's 0, sine x equals 1/2. Now we are looking only on the interval 0 to 2 pi. We're looking only on this interval. So what values of x satisfy that sine of it equals 1/2? I hear 5 or 6 and 5 pi or 6. Do we agree with that? Okay. So these are potential maxes and mins. Now, do I ever have a time when my function is undefined? No. So we don't have to worry about anything from here. So these are potential maxes and mins. Now I need to test this on the number line to actually know whether they are actual maxes and mins or not. So again, I'm testing this on my number line with my first derivative. And you know what, we're only going from 0 to 2 pi, so I'm going to limit myself here. They don't always give us an interval, but stick with it. And we've got pi over 6 and 5 pi over 6. Alright, so now I'm just simply checking the sign of my derivative. So I'm putting it back into my derivative. So then you know my derivative is positive when it's negative. Alright, now, again, we're comparing it with my first derivative here. Before we got to deal with factoring, which made it a little bit nicer for us. But here we are dealing with our sine function. It's not factored, so you do need to actually think of what the value is and whether that's going to give us an overall positive or negative. So make sure you do know your sine values. Alright, so between 0 and pi over 6, what are we going to get when we take that value and put it in? And again, you can choose what value you're putting in. But if we know our unit circle values, anything, because this is pi over 6, right? So what is the largest that sign is? 1/2. Alright, so when I pick something between 0 and pi over 6, do you agree I'm going to get something smaller than 1/2? Right. So when I take that and put it in, would you agree overall we would get a negative value? Does that make sense what just happened there? Reasoning through that. Yeah. So I know that so my starting point here is 1, 0. And my sign are my y values. So between 0 and pi over 6, which is where we're looking, my value from 0 to 1/2 is my value from 0 to pi over 6 is going to be between 0 and 1/2, my sine value. So when I pick a number in here, you can do pi over 12, whatever you want. We don't really know the exact values very well. But when I take that value and put it into my equation here, I know that sine of anything within here is less than 1/2. right? It's between 0 and 1/2. So that number minus 1/2, this will be the larger value, so we end up having the overall number. Does that make sense?
Can't you just choose 0 because it's in the interval?
I want to say yes. I'm gonna go with, yeah, we can, because this is our relative maximum mins, and 0 is not a possible relative maximum, right? Yeah, so we could do that. That would be even faster.
Good job working smart.
So Reed asked, could we just use 0? It is within my interval. And again, 0 was not a possible maximum, so we can't use it as a testing point. If it was a possible maximum, we wouldn't be able to use it. Good question. All right. Other questions so far on how we got that guy? Okay. So now we need to check between pi over 6 and 5 pi over 6. What quadrant does 5 pi over 6 leave us in? What quadrant? Oh, you said second. They said 6. There's only 4 quadrants. Okay. So 5 pi over 6 would be here, right? Okay. So again, we're taking that sign value. So you pick anything in between there. Take that value and put it in. Personally, I like this guy because the numbers are nice and easy, right? What is sine of pi over 6? 1. So 1 minus 1/2 gives us an overall positive. Does that make sense what I did with that? Takes a lot more thinking when we have the truth. Alright, and then between 5 pi over 6 and 2 pi, again, you get to pick whatever you want within there. You could go with either this guy or this guy. I'm going to go with this one here. Because what is sine of 0? 0. And so 0 minus 1/2 gives us that overall. Is everyone good with what happened there with our number? A little bit more work with trig than just with that. Okay. So then I can go ahead and identify my relative maximums here. Alright, so what is pi over 6? Sorry. At pi over 6, we have a relative max or a relative min. Good. We've got a negative slope to a positive slope. So I have a relative min at x equal to pi over 6. How about at 5 pi over 6? Positive slope to negative slope. Good. So I have a relative max at x equal to pi over 6. 5 pi over 6. Now they want us to find the actual relative max and relative min. We will do that in just a moment. But now we found where they occur. How do I find the actual relative min and the actual relative max? Yeah, we just take those values and substitute them into the actual equation. Which we're going to do that for absolutes anyway. Are we good with relative max and mins and where they occur?
Remember the point where it's both of us?
So there is a situation where it's just a horizontal line. So let's say this thing here. But I have to double check and look back at the definition. I can't remember. I think this would be that just neither has maxes nor mins, or it is both the max and the min. I can double check and see. I need to look to see if the definition is that it's higher than every single point around it, or if it's higher than or greater, if it's greater than or equal to. The question is going to be equal to. So I have to look at that. Alright, so then it asks about absolute max and mins. Now, absolute max and min, I need to not only consider these relative ones, but also my endpoints here. Alright, so this is where we go ahead and compare it on our chart. Because I know that this is where we have humps and valleys, but I need to know which one's the actual highest hump and which one's the actual lowest valley, as well as compared to my endpoints here. So I have 0, pi over 6, 5 pi over 6, and 2 pi. Alright. And I'm going to cheat and go a little bit faster. And we have at 0, it's -1. At pi over 6, negative square root of 3 over 2 minus pi over 12. Yikes. So that ends up being negative 1.138. Using a calculator for that guy. 5 pi over 6 gives us negative 0.443. And 2 pi, negative 4.12. Alright, so if we look here, which one gives us the highest value? Good. So this is going to be where my absolute max occurs and what it actually is. And which one gives me my lowest value overall? Good. So this is going to be my absolute min and where that occurs. Alright, so I'm going to write that down here. Absolute max of negative 0.443. And that's at the point x equal to 5 pi over 6. And absolute min of negative 4.142, and that's at the point x equal to 2. So here we had one of them came from a relative and the other one came from our endpoint. They could both come from relative, both from endpoints, or either. The original one here, yeah, because we want to know on our original graph, is that the highest value, the lowest value on the original graph? Absolute maximum value, minimum value of the original graph. Good question. Other questions on the absolute maximums? Okay, so you need to know your relative maximums in order to test those. And then next we have points of inflection. What is my justification for points of inflection?
Double prime is 0 or undefined.
Good. So when we are entering into points of inflection, then I'm looking now at my second derivative. So my second derivative is equal to 0 or undefined. What else does my second derivative tell me about my original function? Good. So concavity also comes from my second derivative. Alright. So let's do points of inflection next. So I need to know my second derivative. I think my second derivative actually has to be even nicer. Golly, there's so much going on here. Cosine x?
Yep.
Alright, so then for points of inflection, I check when my second derivative is equal to 0. And when it's undefined, so I'm looking when cosine is equal to 0. And what values on this interval would that be? Pi over 2 and 3 pi over 2? Are we all good with that part? Okay. Can I ever have my cosine x be undefined? No. Okay, so these are possible points of inflection, but now we need to test it. How do I know whether it actually is a point of inflection? What do I have to do with it?
The sign changes.
Good, where my sign changes. So for point of inflection to mean not only that it's equal to 0, but even more so that my second derivative changes signs. And in fact, in our justification, we can skip the fact that it equals 0, because that by itself is not enough. We want to focus on whether or not that second derivative changes signs. So equaling 0 gives us potential points of inflection. Testing it allows us to see if it actually is or not. Alright. So my second derivative number line I'm checking. And again, we're only going from 0 to 2 pi. So I have pi over 2. And 3 pi over 2. And this one's so nice to think of because we're going back to my second derivative. So we've got 0. Alright, so from 0 to pi over 2, what is cosine? Positive. From pi over 2 to 3 pi over 2, what is cosine? Negative. And 3 pi over 2 to 2 pi, what's cosine? Positive. Alright, so we can see we have points of inflection. X has points of inflection. Would not abbreviate on free response, but at the same time, we are here. At x equal to pi over 2 and 3 pi over 2. Okay, and now we can finally take our information from our number lines and translate that all into our intervals of concave up, concave down, increasing and decreasing. What's my justification for concave up? What's positive? It's second derivative. Remember, we have to specify what function we're talking about. And what is my justification for concave down? Good. Second derivative is negative. All right. Then what is my reasoning, my justification for my function increasing?
Prime is positive.
Good. My first derivative is positive. And how about for decreasing? First derivative is negative. Again, justification is really important that you know these. All right. So now let's go and translate all this. So from my second derivative, I can know concavity. F of x is concave up. What are my intervals for concave up? 0 to pi over 2. And 3 pi over 2 to 2 pi. You know what? I'm not going to include those endpoints. It's fine if you do. Alright, and then let's go and do concave down. Did you guys fit this all in that space there?
No.
Yeah.
Who said yes? Interesting. Bart, did you actually fit it all in there? Alright, what's the interval in which we're concave down? Good.
And they're open brackets.
Yeah, just because it's a shared pointer, but they're not picky about that. Yes.
So, is there an actual point inflection, or sorry, can you attribute concave up and concave down to point of inflection?
No, because point inflection is defined as where it changes. Yeah, so guaranteed pi over 2 and 3 pi over 2 will not be included. Now, it's debatable as to whether or not you do include the endpoints. I'm just going to go with an open bracket. Alright, then I think our last thing was increasing, decreasing, right? So that comes back to my first derivative over here. And so we can say f of x is increasing wherever that first derivative is positive, and so what interval would that be?
Pi over 6 to 5 pi over 6.
Good, pi over 6 to 5 pi over 6. And it is decreasing. We got two intervals for this. 0 to pi over 6. Good. And pi over 6 to 2 pi. Alright, so pretty much these are our answers. So everything you could possibly want to know with your first and second derivative tests, all your information about first and second derivatives, again, just in a trig situation. Same information as before, just now we're dealing with that trig, which as you can see sometimes requires you to think a little bit deeper as you're plugging in checking points. Alright, questions with all of that? Okay. If you want to do the other ones for practice, the answer key for that is up on Blackboard for your convenience. But let's go ahead and take a look at your fake quiz you did for homework and questions you had on that. Alright, we'll go over the three response together, but as far as multiple choice goes, let's go ahead and write those up on the board like we did before so I know which ones to give priority to. Alright, let's go do a few multiple choice and we'll go for response and come back to multiple choice. We're going to start with number 8, or 4. Let's go 4 because that's non-capital. Alright, so number 4, we are taking the derivative of an integral. Derivative of an integral, what do they essentially do?
I don't know.
To each other. They kind of cancel each other out. They're opposites, they're inverse operations. So they kind of cancel each other out, but we have to consider dealing with change. So derivative of an integral, where I see that I have that function is defined as one of my intervals, or one of my limits there. I simply take that and substitute in. So I have square root of 1 plus sine x squared. But then what I have to do after I've substituted my function in? Good, multiply by the derivative of that function. Derivative of sine is cosine. Now, if I were to take 2 and substitute that in, I would have then square root of 1 plus 2 squared. But what's the derivative of 2? 0. which is why that whole thing cancels out. We don't have to worry about it. Okay. So again, you can go ahead and go through that generic, the more general process of top substituted in chain rule minus bottom substituted in chain rule. But whenever you have that constant, that's automatically going to give you an overall 0 for that value. So we have then cosine x times the square root of 1 plus sine squared x. And that ends up being d, I think. Yeah. So again, whenever you see that derivative of an integral, and you'll always find that you have a function in one of your bounds there. Okay, so derivative of an integral, because they essentially cancel each other out, which is why I can just take that and plug it in. So I have just my function left over, but I have to consider chain rule there. Alright, questions with that one? Okay, so then we've got number 8. Alright, calculator piece. So at time t equal to 0, the acceleration of a particle is given by this guy here. At t equals 0, the velocity of the particle is -2. That screams initial condition. So I have v of 0 equals -2. For what value of t will the velocity of the particle be 0? So what is this asking for me to find? X, right? We're trying to find x, which, or in this case t, the time at which the velocity is 0. So we're trying to find the time at which my velocity is 0. Are we good with that? What we're trying to get. Okay. Now they gave me acceleration, so I need to find velocity. How do I find velocity when given acceleration?
You integrate it.
Yeah, we integrate it. Alright, now here they gave us a function we can actually integrate, t plus sine t. So I'm going to go and write that in there. And remember, you can't have your calculator do an indefinite integral for you. You have to be able to do the indefinite integral. Now, we've dealt with before where we had our initial, or sorry, our final velocity equals that initial plus the integral of that acceleration. But the reason why I can't use this here is because I know my initial, but I don't know what time frame I'm going over. I know I go from 0, but to what time? We don't know what time, because that's what we're trying to find. So that's why I cannot use this approach, because I don't know what time I'm trying to find that final velocity. So we're just going back to bare basics. The antiderivative of acceleration is my velocity. So I'm integrating. Antiderivative of t is t squared over 2. What's the antiderivative of sine? Good, negative cosine. I'm going to go ahead and put that negative. And what else do I need? Plus c. Okay, because I'm doing my indefinite integral, so I should have a plus c. Now, I use that initial condition to help us solve for c here. So my initial condition says that when time is 0, my velocity is -2. So I get -2 equals 0. What's cosine of 0? Cosine of 0? 1. What did you ask? So they told me that I'm taking this initial condition and plugging it in. So when time is 0, my velocity is -2. So I'm putting it. Alright, so then I get that my initial condition, or sorry, my plus c is actually -1. Are we good with that so far? Questions on that? Okay. So now I have my actual velocity equation. So t squared over 2 minus cosine t plus c, which is -1, so -1. So here's my actual velocity equation, and I want to find when this equals 0. So I want to know when this equals 0. At this point, I would recommend just putting this in y1, this in y2, and find where they intersect, or just simply graph this guy and find the 0 on your calculator, right? And when you do that, you end up getting an answer of 1.47 something. Okay, so again, you had to do your actual calculus by hand to find the general equation for my velocity. Then you had to use the calculator to find when that actually equals 0. Questions with that one? Okay. Let's go take a look at number 10 while we're on this page, and then we'll take a look at first response. Alright, so number 10, find your derivative when y equals 0 if x cosine y minus sine x minus 2 equals 0. So let's go and find our derivative. Have to do with implicit differentiation. So I have second stays times derivative of the first plus first stays times derivative of second. Derivative of cosine is negative sine y. Inside stays, but multiplied by the derivative of the inside, which is just dx. So that's all just the first piece. And derivative of negative sine x will be minus derivative of sine is cosine x. Derivative of negative 2 is 0. Derivative of 0 is 0. Alright, now we want to know the derivative specifically when y is 0. But they didn't give me my x value. So I know what my y value has to be. But I don't know what my x value is. How do I find my x value when given the y? Just plug it in. So I'm going to go do that off the side here. X cosine y minus sine x minus 2 equals 0. So when y is 0, we have to find our x value. Alright, cosine of 0 is 1. So I get x minus sine x minus 2 equals 0. And that you're going to want to use your calculator for, and you end up getting like 2.554. Now, I would recommend using the store button on your calculator so you can store the whole thing in. Do we need to recap that store button? Okay, let's take a look. Remember, you can use your calculator to store some crazy long decimal like that.
Doesn't it give us negatives?
When I do my product rule here, so first is derivative of cosine y, derivative of cosine is negative sine y, dy dx.
Looks like we were doing some crazy math before.
Alright, so again we had x minus sine x minus 2. We wanted 1 equals 0. So second, calculate my 0. Left bound, right bound, I'm going to go extreme and go like 6. You guys can scoot your arrows back and forth. I like to just look at those two numbers. So I get x equals 2.554196. Now when you quit and go to your home screen, you could go ahead and type in 2.554196 and store that in for whichever letter of the alphabet you choose. I would probably just use X since you can do that there. And then you would hit enter. But the cool thing is that whenever you find a value from your graph, so again, I just stored that in for X. I could have stored that in for alpha V if I really wanted, whatever letter you like. So anytime you type that letter, you're going to get that number. Okay. But what's really cool is if you find a value from your graph. So for example, again, I found that 0. Whoops. Let me try again. 0. Left bound. Right bound. So when it finds that, it automatically assigns that to your x value. So when I quit and go to my home screen and just type in x, it'll automatically have that from your graph. So that's pretty nice that you don't have to worry about sorting that in. But you're welcome to just type this one. All right, so that is the x value that I'm using within my equation here. Now we want to know dy dx. You could go ahead and substitute in and then solve for dy. I'm going to go ahead and solve for dy in this first place. So I would first add my cosine x and subtract my cosine y. And then I would end up dividing by this piece here. Okay. So now when I do my derivative specifically at that point, and that point was 2.554, 0, I end up getting cosine of 0. Oops, sorry. Cosine of that x value, so I'm just going to leave it as x since we have that in the calculator. Cosine of 0 over negative x sine of 0. But when we do this, what does sine of 0 give us? 0. So we end up getting 0 in the entire denominator. And what do we have when it's a number over 0? Undefined. So that's why we end up having undefined. If you take these sides and substitute them in here, you end up getting that this goes away because it ends up being 0, and then you have no dy dx to solve for, which is also an indication as to why it's undefined. Questions with number 10? Okay. I take it back. Let's go back to 6, and then we'll go look at other slides. All right. You guys are going to love this one. So what's sine squared plus cosine squared?
1.
What's 1 squared?
1.
What's the inside derivative of 1?
Oh no.
Oh, wow.
I like you. Pick that up.
I mean, you could have done a lot more work, but that's your easiest way. Questions with that one? Okay. Alright, so let's take a look at the free response. We had a rate in, rate out problem, as well as Karen riding her bicycle with a C. Alright, so for part A, it's asking for the acceleration of Karen riding her bicycle. Now they gave us the graph of velocity. Acceleration is just your derivative. And what's another word for derivative? Slope. Good, we're ready to change. Slope. And so I just simply find my slope at that point. When you do your slope at that point, you end up getting negative 1/10. And then don't forget units whenever they ask for units. Part B, it says explain the meaning of the absolute value of the t being integrated. As soon as you see an integral of absolute value, that should scream to you, total distance. Oh, I'm so glad it screamed to you as well. Alright, so in order to evaluate that, you had to actually find all your little areas and add those together. And this was a calculator piece even. Remember, always show your setup and then your answer. So this integral represents her total distance in miles, so always give you units, in miles, in the first 12 minutes, or you could have said from time t equal to 0 to time t equal to 12 minutes. But make sure you always give units, both for the distance as well as for time. And it ended up being a whole bunch of adding together, and you got 1.8 miles. Are there questions on A or B with that? So again, A was just simply finding the slope because acceleration equals my derivative of velocity, which is just simply yours. Alright, I love part C. Shortly after leaving home, she realizes she left her calculus homework at home, and she returns to get it. This was an actual AP free response question. I enjoyed it. At what time does she turn around to go back home? Give a reason for your answer. So remember, when you change directions, your velocity not only has to equal 0 at some point, right? Because you have to stop to turn around, however brief it may be, but you have to also change signs. So if she was headed towards school and then stopped and turned around, that means that she was going in a positive direction. She stopped, turned around, and is now going in that negative direction. So we're looking for that change in sign specifically from positive to negative. So simply looking at her graph, you see that her velocity was positive all along here. Then she stopped and went in the negative direction, so positive to negative. So we have at time 2, she stopped and turned around to head back home. What do you think is happening from 4 to 5?
She's at her
She's at her house trying to get her calculus number. Okay. And then she finally leaves again at time 5, and finally then gets to school at time 12. So it took her 7 minutes to actually get to school, albeit a total of 12 because she forgot her homework. So let's see. So she turns out at time t equal 2 because velocity changes from positive to negative. And then Larry comes in. I love when they introduce the second person. So now Larry, he doesn't forget his homework. I mean, it doesn't say he forgot, so he just goes straight to school. Maybe he realized and didn't go back to get it. But, so Larry has a different function that mimics his velocity. And they want you to find who lives closer to the school. Well, we know if we were given velocity, we can integrate to find our position. And they're both starting at position 0, right? So they're both starting at their house. So we integrate Larry's function from 0 to 12 and get a total of 1.6. Now, Karen, there's a little bit more thinking you have to do. Because remember, she came back home, and then she went again. So, Karen, I'm not integrating the entire velocity equation. Well, I mean, you can, because we end up having that this cancels out. But couldn't I just simply look at this piece here? Because this is when she heads back to school again, right? So this is when she leaves her house once again, going to school. And this entire time frame is when it takes her to go to school. So you could do it over the entire interval 0 to 12, because these areas cancel each other out, because she went a certain distance and then went back that same amount. But to save yourself time, just look from 5 to 12, because this is when she started from home and went straight to school without coming back. So your area underneath the curve there ended up being 1.4, so Karen's closer.
It's like getting shorter by just using the answer from B and just subtracting the distance from 3 to 4.
Yeah, that would be fine. I like that. Taking your value from B, you said, and subtracting the distance, yeah. Now, do be careful, though. You want to take away both pieces of this distance here, right? What are we doing? Oh, yeah, because that was our total distance. So, yeah, then taking that away now, you would still want to counteract this as well. You want to subtract both pieces there. Because if you take away only from 2 to 4, you're still adding in this distance she went initially before she turned around. So make sure you subtract that as well. So you can just take that away. Other questions with Karen and Larry? Really not. All right. So then here we have our typical rate in, rate out. And they ask, is the amount of water in the tank increasing at a certain time? Well, I need to check my rate coming in at that time and my rate going out. I see that I have more leaving than is coming in. So the amount of water in the tank is actually decreasing. It's not increasing because my rate in is less than my rate. And then B, how many liters of water in the tank? Remember, we have our initial, and then we integrate our rate coming in to tell us how many liters have come in on that time frame. And we integrate our rate going out to tell us how many liters have gone out at that time frame. That's right there. And then for C, write but do not solve an equation involving an integral expression that can be used to find the value of K. So when the water is completely out. At time greater than 5, no water is being pumped in. So again, we have our initial plus the amount that was pumped in during that 0 to 5. And then we subtract how much has been taken out from 0 to whatever time frame. So make sure you don't neglect the subtraction of that. Okay, any questions on those? So your test is next class. Please come see me questions before next class. I'm going to use just some extra review. There's some more integrals. I think there's a free response on there. The answer key for this will be up on Blackboard.
I don't put the video of yourself with.
Is it not up there?
You only have the first one.
Yes. I'll make sure you have it.
Are you watching home?
Yes.
Are you watching home?
There's a teacher actually in my classroom, so I have to be able to
If you want.
Well, yes, you must check them.
Actually, I'm pretty sure we took them all in class.
We